It is a great honor to have Amit Sheth here at this conference. Amit Sheth need not to be introduced, I think, to the DEXA community. Amit Sheth is known as an eminent educator, researcher, and entrepreneur in our fields. He is the founding director of the university-wide Artificial Intelligence Institute, AIISC, and professor of computer science and engineering at the University of South Carolina. And he is elected a fellow of the major professional societies in the area. First, I want to mention ACM, where he was awarded for his contributions to data semantics and knowledge-enhanced computing, this fellowship. And we have in this audience both the ACM president, Gabriele Kotzis, and also the secretary and treasurer of ACM, Elisa Bertino. Then he is a fellow of AAAS, the American Association for the Advancements of Science, for his pioneering and enduring contributions on information integration, distributed workflow and semantics, and knowledge-based big data analytics. Also a fellow of AAAI, the Association for the Advancement of AI, for his significant and enduring contributions to semantics and knowledge-based techniques to transform diverse data to insights and actions, and also of IEEE for his contributions to information integration and workflow management. His awards include also the IEEE Research Innovation Awards, etc., etc. He is also listed, and that is very important for us here at DEXA, as among the top most cited computer scientists. In March 2021, his H index was 107, with more than 49,000 citations. He is also a founder and entrepreneur of innovative companies. He founded the first, I would say, semantic web company, Tali Semagic, that pioneered technologies which are very similar to what is found today in Google semantic search and knowledge graphs. And his fourth company, his last company, is the foundation of Cognovi Labs, a company at the intersection of emotion and AI. And as DEXA, we are very proud that Amit has been contributing to DEXA since 1997, at this time on workflow process automation, where he also won many, many awards, as I mentioned before. And he was also the DEXA general chairperson for the DEXA conference in 2017. So we are now very much looking forward to his keynote on Don't Handicap AI Without Explicit Knowledge. And I see on the screen the brain, and I think that will be perhaps exactly about us, where we use both hemispheres. One, the emotional one, where we are doing a lot of data mining, but also the one place we are doing some logic. So I'm very much looking forward to an inspiring keynote. Amit, the floor is yours. But before starting, I want to mention that this talk will be streamed at YouTube. I hope that this will be okay for you. Amit, the floor is yours.
Thank you very much, Amit. Thank you, DEXA community, for inviting me again. Delighted to see Elisa in present here. I wish we were all meeting in somewhere in Europe and be able to be in person together. We are going to do the best we can in this remote setting. I'm going to talk about something that is very exciting. I hope we have seen amazing progress in AI in some regards, and yet there is a long, long way to go. Um, so, okay, why is my okay? Yeah. So, my talk is about what is there still to come, and what is still missing in the AI today, in spite of some of its progress. We've seen some people claim that give us all the big data and then we'll give you whatever you need to know or whatever you need to do, and we can predict the world, we can predict the future. So people have said big data is enough and that deep learning is going to do everything. There are others, I belong to that other category, where we think that the data alone, data-centric future is hyped, that there is a lot more that is necessary beyond the data. And ultimately, we are working towards different visions of computing that, on one hand, is a vision of machine replacing computer, sorry, computer or machine replacing humans. To other hand, where computing is there to make human life better. So there has been a wide, range of vision for AI, and I belong to, those who are looking for AI as very much supportive of improving human life, but not necessarily so much as to replace. Now, so among the people that have said that no, big data is not enough. For example, Pedro said data alone is not enough, and that we need, or Gary Marcus saying we need to build AI that captures how human thinks. So an example that comes to my mind, take, during the election, let's say in US election 2016, some of us had access to so much of the data, all the polls, all the social media, all the news article. But even if you had fed that into a computer program, that would not have predicted the outcome. A majority of the, almost all, had predicted that Hillary Clinton would win. Well, Donald Trump won. Now, I was able to predict that Donald Trump will win, but that was through a symbiosis, a combination of all the data and applying my own understanding of a lot of things, the politics, the geography, how the electoral system works. All of them had to be used in interpreting the data correctly to get to that prediction. So humans, as I thought about the activity that I was engaged in, and by the way, this was done using Petri system that became the fourth company I founded called Cognovi Labs. It showed me that data alone is not enough. And this was not the only time that we had to do this way. We predicted Brexit, we predicted many other election outcomes. So if you look at AI systems today, it's pretty good at some of the things like, activities like classification, some prediction, recommendation tasks, language processing, and text generation is very good, language translation. But there is a lot more to higher level of human intelligence or machine intelligence. You want machine intelligence of the type that is similar to human intelligence. So AI is fairly good at some well-defined, narrowly defined tasks. Human is very good at broad spectrum behavior. And our, intelligence is broad, complex, and multifaceted. A lot of things that go into human intelligence. Correspondingly, data alone won't be enough. We will need to have knowledge. So there are a number of high-level capabilities that I and many others would like to see in future machine intelligence. And they include things like abstraction, contextualization, personalization, analogy, causality. These are some of the some of the capabilities that are largely missing in the current AI systems. And the whole, I guess I'm going to pass some of the slides I have. What we are looking for is to expect more from the machines. So we need better form of machine intelligence. And the point is knowledge is needed to achieve that high level of intelligence. Now, today, over the period of time, we have seen that we had the phase one of AI in the last century, where symbolic, it's also called symbolic AI. And we are coming towards the end of the phase two of AI, which is being referred to as statistical AI. My hope is, and expectation is that knowledge will play the central role on what is there to come. So there is an article we recently wrote, the duality of data and knowledge across the three waves of AI. And some of us, many of us believe that we're kind of entering the third phase of AI. We need to develop AI systems that innately grasp basic concepts like time and space and geography and spatial things, knowledge and experience, and causality in a way human minds think. So here is a sentence on the right. Xanadu quit graduate school to join a software company. And if a human interprets this language and what we call as language understanding, then the human would know Xanadu is a living young human adult. He's a graduate, he's in a graduate school, he quit the graduate school early, and he joined a software company that needed a new employee. All of those things humans would be able to construct. But how? Well, just from the data, which is what is shown in the right hand side, you won't be able to get that. You would need to use the knowledge that you have. You have common sense knowledge, you have knowledge of the world in this general area. That is what will enable you to have the understanding that is shown the left hand side. So one of the things involved here is common sense. People in other fields have talked about some very important concept in the context in the cognitive science literature. You hear about top brain and bottom brain. In behavioral economics, in Daniel Kahneman talk about thinking fast and slow. And so there is this concept of system one, which does perception and is closer to statistical AI. It thinks very fast. And system two, which thinks slower, is cognition, is closer to symbolic AI. Our brain does this very, very well. And this is key to our intelligence. Knowledge and experiences humans have play extremely important role in enabling combination of both of these, which is a hallmark of human intelligence. A few years ago, I wrote an article, and in 2017, another keynote I gave was on semantic, cognitive, and perceptual computing. Right now, I just want to show you one important thing that is the right side of this picture. So this picture, is about an example from pediatric asthma patients. We have data from of all kinds. exhaled nitric oxide, or how the lung functions, how much sleep you got, what is the pollen outside, or what is the quality of air that can affect a child's asthma, and so on and so forth. So on the bottom, you see, bottom right, data. But through series of activity, I would call abstraction, you get what you see on the top right. You get to understand whether the child's asthma is poorly controlled or well controlled. And that is the level of abstraction that is important for humans, for human decision making. A doctor who performs asthma control test will ultimately come to a conclusion of this kind. So the data at the bottom is really not very important for decision making per se by alone. You need to transform it into the form for human decision making, for human to act upon. And in this whole process also, the role of knowledge was extensively described. Another point I want to make is that humans use a broad variety of knowledge. So it's not as simple as just using information, let's say, about asthma. You have to use information that is a domain specific knowledge, and yes, that is important, but you have to use common sense knowledge. You might use that individual own experience as well as social norms. You might also need knowledge about the law and policy. So and we discussed that in an article called knowledge graphs to empower human inspired AI systems. So the knowledge that so we want to use knowledge for endowing machines with high level of intelligence. With the knowledge, we are going to be able to explain and predict well beyond current capability of statistical AI. Knowledge can capture common sense and underlying knowledge, and knowledge can be very important for disambiguating, for making sense between different interpretation of the syntax of the words of the text. So machine intelligence, so in a way, I'm going to take an example to make the things that I talked about so far more concrete. Look at this text in the middle. It is a text from a web forum post. There are a lot of things in this text. One example, interesting example, is that the text has terms like Suboxone and Bupe. Now, it so happened that in this corpus, for every one occurrences of the concept called buprenorphine, which is a drug, opioid, there were 33 occurrences of a variety of terms that had the same meaning. So buprenorphine, you look at top left corner, you'll see Subutex and Suboxone, which is brand name of buprenorphine. You see Bupian and Bupe, which is slang or street names. Now, with all that different varieties, it is extremely hard for a pure data-driven system to understand that they are exactly the same, especially when there is a sparsity of data. But if we have a knowledge graph, in this case, we have drug abuse ontology, which explicitly models all of this. This ability to understand all the variety of the same term with the same meaning becomes much more doable. So you could have far more recall. But more importantly, you would have deeper understanding of the content. So when you look at this content, you want to understand a lot more things. You want to understand dosage. For example, 2 milligram dose of Suboxone. You want to understand what that is. You want to understand the time interval. You want to understand relationships. You want to understand sentiment. You want to understand the route of administration, like inject. So the understanding of the language is more demanding, and pure statistical techniques will not work very well. This is where the use of knowledge, in this case, I'm showing the use of common sense and domain knowledge, becomes very critical. Think about your, I'm speaking something, and you understanding what I'm saying, and think about all the things it takes for human brain to understand somebody else's language. You have knowledge of English grammar. Remember, lawyers can talk about where the comma is, and then decide the meaning. So parsing of a language, of a sentence, is a very important thing, and that is the knowledge we apply. We have linguistic knowledge. So for example, and something like, WordNet is a very good example of linguistic knowledge. We have common sense knowledge. So you could get some common sense knowledge in ConceptNet. We have broad and general purpose knowledge, such as the knowledge we get in Wikidata. And we have domain specific knowledge, such as knowledge about drug abuse, prescription drugs, asthma, or whatnot, right? One comment that I will make on the side for those of you who also work on NLP is that the artificial intelligence community currently and the NLP community has set their sight very low. So the glue and super glue kind of standards, the tests that they have developed are really not deep understanding kind of, they don't measure deeper understanding of language. They are largely syntactic and low level understanding of the language. What we need to be able to do is to go to the human level understanding of the language, and we need to set a higher standard for our AI system. So that's one of the activities going on in my group. So let's look at what we call as knowledge infused language understanding task. On the left hand side, you see some conversations going on, the human says in blue, "Tell me about Bube." The system has no understanding what it is. On the right hand side, when the human asks, "Tell me about Bube," well, the system knows what that is and can further engage in the conversation. This conversation becomes a lot more possible because of the knowledge of the domain. Here, on the left hand side, think about a chatbot. And chatbots today, many of them are found to be very of limited use. There is quite a bit of dissatisfaction with the chatbots that we have today. Chatbot, can tell you what weather is today if you were to go outside. But with personalization and contextualization, if the AI system knows that you have asthma and that you are allergic to ragweed pollen, and that today ragweed pollen is high, then it could advise you with something that you can act upon, such as take your rescue medication, right? Or not go out, right? So there is a concept of, here we talked about personalized knowledge graph. So imagine that the system understood from all the conversations that you have had for the long time and incorporate that in understanding what you need. Now that system would be very helpful. It's like a child has an asthma and a parent is helping child make the right decision. and parent has understanding of all the history of the, of the child with regards to asthma, and hence that can be factored in the decision making. That knowledge is critical for making the system intelligent enough to help a human. So among the, here we are, this is an example from a mental health virtual assistant that we have built and are further building and advancing, which supports personalization, abstraction, meaning mapping patient features to human understandable concepts, and continuous contextualization. Day to day, time to, hour to hour, a person who suffers from anxiety or depression or some mental health situation will vary, and you'll need to be able to keep up with all that if you're going to be able to help the person, right? So continuous contextualization is also an activity that you will need to support if you are going to really support the human. There are many domains besides natural language understanding, which I talked about, where we require better intelligence. So here I have put some examples: self-driving cars, conversation with a patient, effective education pedagogy, supporting social good, for example, countering anti-vaccine message. In all of these kind of activities, we need high level intelligence, and in turn that will need knowledge. Here is one simple example again where I try to show you why knowledge plays huge role. This is my theory, but think what is happening as a human brain is exposed to simultaneously a speech, text, visual imagery, video. Our brain is able to seamlessly connect all of them. The theory is that that connection is not happening at a pattern level alone. That the system one does its work, and then while going to system two, the connection happens. In this particular case, we took data from the entire Bay Area of US, road network data. On the, you can see the waves and the traffic pattern you are seeing on the right side of the image. And we also tapped into Twitter data, which where people talk about accidents and whatever, weather and everything. This example shows that there was a traffic slowdown at a particular location, and that we were able to connect tweet from that area that were explaining why there was a traffic slowdown. Now, so this is what you might call as multimodal understanding, multimodal machine learning. But if you are trying to do just the machine learning on that, it is incredibly hard to connect these two highly diverse data from a relatively small set of data sets to train. The number of traffic incidents and that you can train from is very limited. But if you have a knowledge base available, a knowledge graph available, that has the ability to connect these two different type of modality of slow traffic and accident. So here we had three knowledge graphs, including a knowledge graph about traffic, and you in that knowledge graph says accidents lead to traffic slowdown. That kind of knowledge becomes very helpful in connecting this very diverse data. One very important example, that also would demonstrate the important role of knowledge is abstraction and analogy. So you see here in this picture, there are a bunch of examples along what we call as abstraction ladder. So the things at the low level, at the bottom, are lower level of abstraction, and the things at the higher level are the higher level of abstractions. Human brain is very, very good at doing that. I am not aware of an AI system that can do that very well. So one of my, somebody I know very well, a professor in chemistry, use analogy to teach undergraduate biochemistry in his class. And he asked his students to create analogies to describe scientific concepts. So the scientific concept is how electron transfer chain is works to convert energy in the human cell. And then the student gave an analogy where a villager uses a string and uses his energy to get the water. That water flows down to turn a turbine, and he makes a wonderful analogy between these two concepts, which then makes it easier for the students to understand this biochemistry. This requires systemicity and process constrained sequential process knowledge. It will be incredibly hard, or I would say nearly impossible to do purely by statistical means. So here this one shows how one can use the knowledge representation to help create this analogy and to help understand this analogy. So rope is electron transport change. Villager pulling rope provides energy is equal to electron transfer on transport chain provides energy, and so on and so forth, right? And the way we are approaching this is that the students' analogies are in text. There's a class book text that talks about the energy production in human, the electron transport chain and energy production in human cells. And there is a text that human has written, a child has written, a student has written about the villager and pulling the well. How do you now build a system that says how good this analogy is and help the teacher understand whether the analogy is good or bad? So we are doing work on analogy understanding, where knowledge graphs plays very important role. There are many types of knowledge that are necessary, and that they all, we humans use this very well for future systems, for better machine intelligence. We'll have to find a way to represent and apply all of this kind of knowledge. Knowledge also enables us to think, create abstractions, act. So for example, we do reasoning over concepts using relevant knowledge compiled during a thinking phase that results in action, and then decide, executing action to enable decision. So these are, if you think about it, these are the things that humans do all the time. These are things that we like the machines to be able to do. Today's AI systems don't do this very well, and knowledge will be critical in doing that. Another very important topic is the interpretability and explainability. 91% of the companies have said in one survey that they want the AI system to be explainable. Current interpretability and explainability that you get from statistical AI system is rather limiting. So, excuse me. Machine learning models provide interpretability through this parametric visualization method. That's one of the popular methods. Now, that itself is not good enough to construct an explanation that end user or a decision maker would be happy with. So knowledge traceability would provide explanations on the model outcomes in terms of concepts that the domain experts or even end users can understand. So the idea here is that without the use of knowledge, it becomes incredibly hard or impossible to construct an explanation in the form that the humans can use. So over the recent years, we've been working on what we call as knowledge infused deep learning or knowledge infused learning. This is our attempt to combine the system 1 to system 2 or build these neuro-symbolic systems. Neuro because we are doing statistic AI, deep learning systems, and symbolic because we are using knowledge graph. So there are many ways that you can combine data and knowledge, which is my main message in this talk. There is a shallow way you combine the two. This is to essentially take knowledge, put it in the form that statistical AI system does. So largely today neural networks work on vectors. And so what you can do is to convert the knowledge into a vector and then combine the vectors. And this is called knowledge graph embedding techniques. They become very popular and they have shown some benefits, but there's a lot more that can be done. So there is a semi-deep infusion technique that and a class of techniques that occur. And by the way, these techniques work with all kinds of deep learning methods, and we have worked with LSTM and CNN and adversarial learning methods and so on and so forth. So with this one, the knowledge is used, external knowledge is used to change the attention mechanism and improve upon the performance of the transformer model. And it typically works at one layer, usually a output layer. Now let us look at this example again, just to give you at a high level understanding of what these knowledge infused learning do. Here is an example of text from Reddit, and the question is what kind of mental health issue this text talks about. Basically classification, and the state of the art technique here classified this to be depression, and it says, is it mental health related? It says probability yes is 0.71, so 71% it is sure that it is the following, and it gets false, which is wrong. What we did was to take knowledge from the mental health literature. So the DSM-5 is the documents that mental health professionals use for their training to become mental health professionals. So from that you extract concepts, organize them in a knowledge graph, and then you create, in our case, we created a matrix and then combined with a statistical extraction, a pattern, and that led to this classification. Here now we were certain 96%, we had 96% certainty, and the prediction was the correct prediction of OCD, obsessive compulsive disorder. So besides that, this particular process also provided interpretability and explainability in the form that you can use. So here in that you see the text and you see the semantic annotation. So the text concepts in the are identified and linked to the concepts in knowledge graph. This is called also lifting. In semantic web community, we all know this very well. On the top right is a definition of OCD. It says obsessive compulsive disorder is a disorder in which people have obsessive, intrusive thoughts, ideas or sensations that make them feel driven to do something repetitively. Right. So these are a variety of concepts that define the OCD. How understanding, being able to map these concepts into a knowledge graph allows us to say, okay, here he's talking about intrusive thoughts. He's talking about repetitive things happening in repetitive thing. Need to get out of my head. It talks about some other issues. In this case, there is a bias, high risk by behavior. All of these allow you to map to the to the definition, and thus I can very easily create an explanation. But the human understands the definition of OCD, so my explanation should be similar. And being able to do this, understanding the mapping of language to the knowledge makes that possible. Here is one example from one paper. The left shows state-of-the-art deep learning method, and the graph shows error rate. And then you see on the bottom increasing, adding more features, then adding these contextual features, and then you are excuse me, DSM-5 knowledge hierarchy. You see huge improvement in reduction of the error, and then you add some more details of that, including slang terms, and you really reduce from 30% error rate to 2.5%. So this shows you the power of knowledge, right? And how you can make the statistical AI systems more powerful with that. Now, our theories, this is just my theory, that this cycle of system 1, system 2 is not working at a very loosely coupled level. It's working at a tightly coupled layer. Remember earlier I showed you multiple levels of knowledge graphs, starting with language grammar and lexical knowledge, to common sense, to general purpose, to domain specific. Well, those are the knowledge at different levels of abstractions, at different layers. Similar to a deep learning, deep neural network having multiple layers, we have stratified knowledge. So the idea is to, the point here is that there are different forms of knowledge, and they are relevant to improving the functioning of different layers of the neural network. And so here we are showing you that the knowledge infusion occurs at different layers in the deep neural network, and we call that deep infusion. And that's the process that that is a powerful class of systems that we are developing. Okay, so respecting the time, I did kind of go through some of the concepts a bit faster, but I think I did convey you the general message. DARPA, in the US, have talked about 3 waves of AI. The first layer of AI, which was all about handcrafted knowledge, and they said, well, the system were able to describe. The second way of the AI, we started in this century, and of course the deep learning, really picked up the stream starting 2012. So it's less than a decade old. It's amazing how fast the technology is moving. That is a statistical learning. It's pretty good at categorization. And then DARPA talks about the third wave, contextual adaptation, and can explain. And I gave you the kind of a general view, my belief as to how these kind of systems that can explain and adapt can be built by combining the statistical learning system with knowledge. That would make the systems very powerful. So that leads to my message that explicit knowledge will play a major role in the this early part of the third wave. There's a lot more to go, of course. But one important message that I want to share with you, or one also thing that drives my own research now, is that AI systems ultimately should be built to help humans. Let me describe a class of applications that I'm very involved with. These are applications supporting chronic health disease. So people have hypertension, people have diabetes, people have mental health issues. A large number of 1 in 5 Americans have mental health issues, and probably the statistic goes worldwide. Quarter of the people have some, I forgot the exact detail, but very large percent of people have, I think about 25% people have this diabetes, and even larger number of people have hypertension. So we are building these systems. They are mobile apps, they are virtual health assistants to help the patients manage their health better. In a chronic health conditions, a patient goes and sees the doctor once every 3 months, once every 6 months. But the disease changes day to day. We are building an application for children with type 1 diabetes for a system that will accurately count the intake of carbohydrate that should be monitored carefully for type 1 diabetes children. And so you have food photographs of food that you are eating, and a whole bunch of nutrition knowledge base, and all that have to come together, and current sugar level of the child has to come together, and the target that you want to maintain has to be there also. So in all this kind of stuff, you are constantly engaged with the human, and the human is not going to work with a brittle system. The system that we have to build have to have emotional intelligence, it has to have empathy, it has to have contextual understanding what is happening day to day in the life of the human. It has to be personalized with all the past history and current history of the patient and his disease. It has to understand abstraction, because the human can talk at different levels of details. I'm not feeling good. Well, what does it mean? And all of these have to come together. So to build the AI systems, whether it is virtual health assistants, whether it will be assistive robots, and all that kind of stuff, we will really need to make these systems far more intelligent, and it will have to have human level of intelligence, so that humans will feel comfortable in communicating and conversing with these systems every day, day in and day out, for many days, for months. Many times today we use some AI systems like chatbot, use 1 or 2 or 3 times and then give up. We don't want to use it again. It asks you the same dumb questions again and again. It does not remember what we said. It does not remember my situation. It does not remember what I do typically on this time of the day with regards to this particular activity. So to do all of that, simply feeding the system data is not going to work. We really have to have explicit knowledge of broad variety to make this system smart enough that the humans will engage with them. So let me I have a wonderful team. These are just 3 of the members who helped me to put together this slide deck, and also want to thank a lot of funding from many places. The slide deck has a lot of references and a lot of details that if you want to go into, you'll be able to do so. So with that, let me turn it over to you, Amit.
So thank you very much for this very inspiring talk. And it is exactly the spirit of DEXA, started as a database and expert system conference. So we are dealing with huge amount of data on the one hand side,
Yes.
and explicit knowledge and on the other side. And I think we got the message that we are now going towards the third wave. Yeah? And where the ultimate goal still should be that machine, as you said at the beginning, is not replacing humans, but AI is there for making life better. And we are now reaching the third wave after just describing, categorizing, but to explaining. And explaining will be important, especially if I think about Europe. It is essential because especially in the field of health, as you have pointed it out, there will be even a requirement for explainability.
Yes.
So no drugs or whatever diagnosis, etc., can be just used without explainability or without an extra, as you have pointed out it very clearly, knowledge of the expert. So perhaps just one question. 2 weeks ago, I met our former president, and he was in China, together with the former president of France and the former president of Germany, so Monsieur Hollande and Mr. Wolf. And he was introduced to a female robot. And the French president asked very difficult questions, also the German one. So the Austrian president started to ask something he thought couldn't be answered by a robot. Yeah? So he asked this Chinese female robot, how old are you? And the answer was very surprising, and that is why I'm asking you now. The answer was, didn't you know that asking age a woman isn't polite? So is this already something like this, that there's some tacit knowledge included, or what could it be? Or is it just by accident?
So, this is very interesting. We live in a world of these massive language models. We know the BERT and GPT-3, and Google has even bigger models, and China has even bigger model. So these are language, these kind of systems are, generally speaking, driven by extremely large corpus, with extremely, these millions or billions of parameters that they so-called have. And I will give you an example just of this kind, where a researcher interacted with a system built using similar language model, and asked the mental health question, and the software, the assisting, the chatbot, basically advised the patient to commit suicide. Mm-hmm. Right. So this is a very well reported also example. And what does it tell you? So if you ask them questions that are somehow represented in the language, in the vast corpus, we are there, we're already there, and you will be able to get the answer from that. So think of these as super search engines, basically, of forms. But that's not how humans are. We have amazing amount of variations and exception. Suppose you are this, a woman goes to get a driver's license, and then she's asked question, what is your age? Well, the answer that is impolite to ask won't be acceptable, right?
Yes.
So this is very contextual in nature,
It's
right?
quite a contextual, yes.
Yeah, and these things are currently one size fit all. Another person asking the same question will get the same answer from that robot, but that's not how the reality is.
Yes.
It depends on the two different people. So in my talk, I talked about contextualization and personalization, just two of those things, and those are the kind of things that the systems still don't do well, in spite of amazing power that they have. So they will really what you call surprise us with amazing amount of um, um, information they have created by crunching vast amount of data, but they would simply not be able to perform in the real world. The example you gave, so a lot of my work is with clinicians, and these clinicians won't use AI system because they have to follow clinical guideline,
Yes.
and based on the clinical guideline, they say I'm recommending this treatment, or following this guideline. The AI system may be better than humans in classification task. It may even do better prediction, but the expert clinician won't use it until the system can explain how the process of coming to that conclusion utilizing the medically accepted clinical guideline. That process knowledge must be in the system, which you don't have now. What is that? That is knowledge. Yeah. Clinical guideline is the knowledge, which is what we put in our system. So my talk is about basically saying that, look, we've done amazing job in building this statistical AI systems. They've become very powerful, but they have practically reached the end of it. I and many others disagree with Hinton that deep learning will do everything.
Yes.
And that I presented a lot of counter examples, and others have other examples. And I think that to make the system, even the little things, right? This we know all the issue about changing a pixel changes the classification. Adversarial learning, I kind of example. Mm-hmm. This brittleness, also to remove that, will need the knowledge. Will need to make the system flexible. So there are many things that we can do for which knowledge will become very important part. And I think that another reason for me to pick this talk for DEXA was that DEXA has this history of expert systems. DEXA has the history of, in some sense, of capturing expert knowledge and the issues that experts, how do you build a system that are relevant to supporting expert, decision making.
May I interrupt you? Elisabetino has a question. She just posted it.
Thank you, Amit. Thanks for the nice talk. But I have a very long-term question. Okay, suppose we are able to build the systems as you envision, that they can use a lot of knowledge, but there will be a fundamental difference with humans. They won't be like us, mainly because they will have access to all the knowledge of the world. So in a very short time, they could search large ontologies, file rules, do even simulation. So this will be the real issue that we need to understand, unless you say we need to limit their knowledge. But then again, you say, one has to have a lot of knowledge. This is my first comment. The second, I don't like this distinction a lot between knowledge and data, because in humans, knowledge, how is this knowledge acquired? It comes from sensory inputs, which is data, comes from experience, which is still data. Unless we believe in philosophers who thought that we had innate certain ideas before even, you know. So those are my 2 points.
So our disagreement is about reductionist argument. There is possibility of seeing everything as a data, but I belong to those who do not see it that way because of the humanistic process that happens. So when one of the very important this can be a long debate, but I'll just give 1 or 2 very salient distinction and points. See, when we create an ontology or knowledge graph, it is supposed to have ontological commitment. So it is supposed to have captured the agreement among humans, among the users of that data. This is outside of the data realm. Data is data, you have sensory data, you have observational data, and you can record them in whatever form. And the distinction, I'm not making the distinction as to the data in how you represent data in the system, which could be as a graph also, and knowledge graph, which can represent as a graph, or whether you use metrics or vector. We're not going to that level of issue. We're not going to computational representation of data or knowledge. At that level, everything can be considered the same. The distinction comes where when you develop WordNet, there was a human understanding that was used. When you develop ConceptNet, there was a human understanding that was used. When you do Wikipedia, there is a level of contention among the editors that happens in terms of whether you accept something or not. When the people wrote DSM-5, medical doctors wrote DSM-5, there is a consensus among the medical professional about the thing. That consensus, that humanistic activity becomes the reference point, and that is extremely critical. Now, those reference point could be very large amount of consensus, such as consensus among all the mental health professionals who get trained on DSM-5, or a consensus as in individual's own knowledge as we create in personalized knowledge graph. But the distinction is not at a representation of such level. The distinction is at the level of believability, at the level of endowing this pieces of representation with the agreement among the humans, with the common understanding of the real world. There is a computer world of bits and bytes and all that, and there is a real world. And the real world has sensory things, emotions, many other things. They don't live in computational form, and hence this distinction is very important.
Thank you, Amit. If you can give a short answer, there's a question in the chat. I wonder whether dynamic contextualized personalization, as you mentioned it, means that we actually need systems that possess situation awareness. If you can give a very short answer, because we have to continue in a few minutes for the next session. So dynamic contextual personalization and situation awareness is the question. Yeah.
Yes, absolutely. Situational awareness. In fact, the personalized health knowledge graph is a situational awareness of that patient. If I use the knowledge graph for that is dynamically changing for a hurricane, for disaster coordination, so I need a situational awareness and disaster coordination. I change my knowledge graph continuously with the new things I find, which new area got flooded, and I put that in knowledge graph. Yes. So the answer to your question is yes, indeed.
Okay, Andrea, will you? Is okay for you?
Yes, thank you. That was very, very interesting answer. Thank you very much.
So, not to be impolite, but the next session will start in 2 or 3 minutes. So, thank you very much to our colleague and friend Amit Sheth. Thank you very much, and may I use my hands. Thank you, and I hope that we will meet soon again in not in Zoom, but face to face. Thank you very much, Amit. It was very inspiring talk, and we will work to gain the third wave. Thank you very much.
Thank you for inviting me. Thanks.